Hi students, topic name binary search tree operations, basic operations of binary search tree, create, insert, search and delete. 4 operations we are going to discuss in this video. So let's start. So first operations, so basic operations on a BST. First we want to create a BST from a list of elements. If we have already a list of elements and from this elements we want to create a BST. So this is our list. So our operation is starting from this first element. So this is our root node of our binary search tree. So this is our root node. Then we want to consider the next element. So 15 is the next element. Then our step is to compare 15 and 45. 15 is less than 45. Then we can insert a 15 as a left child of 45. Okay. Next is 79. 79 is greater than 45. So we want to create a node as a right child of 45. Okay, then 90. When 90 is there, we are first considering the root node. So 90 is greater than 45, greater than the root node. So we want to travel to the right subtree. Then we are considering 79, next node. 90 is also greater than 79. So we want to travel to the right side. If right side is null, the right child of 79 is null, then we can insert as a right child of 79 as 90. So 90 is also we are finished. Then we are finished. Then 10. 10 is when we are considering the root node. 10 is less than 45. So it is on the right. The 10 should be inserted at the right, at the left side of this binary tree. So then we are comparing 10 with 15. 10 is also less than 15. So we are considering the next left child of 15, but it is null. So we can insert as a left child of 15. Okay, so 10 is here. Next element is 55. 55 when we are starting from root node, for 55 is greater than 45. So we have reached here. Then 79. 55 is less than 79. So we are traveling to the left subtree, but the left child of 79 is null. So we can insert 55 as a left child of 79. Then the next element 12. 12 is less than 45. So we are going to the left subtree part. Then 15. It is also less than 50. Then again we are traveling to the left part. Then 10. 10. 12 is greater than 10. So we are traveling to the right side of 10, but it is null. So we can insert as a right child of our 10. So that is 12. Then 20. 20 is less than 44. So we have reached here. Then 15. 20 is greater than 15. So we are traveling to the right side, but it is null. So we can insert 20 as the right child of 15. Next is 50. 50 is greater than 45. Then we have reached here. So we are traveling to the right side. Then 79, it is less than 77. So we are traveling to the left part. Then we are considering 55. 50 is less than 55. So we can traveling to the left side of 55, but it is null. So we can insert 50 as a left child of 55. So this is the end of our list. So this is the binary search tree of this particular list. Clear? Next is search operations. Search is very easy. When we are considering the search operations on a BST, it is like our binary search. What is binary search? Binary search is implement only on the sorted list. So we are considering the item, and if it is, when it's a mid value we are considering, then if it is greater or smaller, we are only considering one part of that list. We are ignoring the other part. Like that also we are doing the search operations on BST. So search algorithm is looked like this. So root and item, we are starting from root. So it is act as the mid value for our binary search. Okay. Just comparing binary search tree, search and binary search. Okay. Next, first step is if item equal to root data. If we want to search, our item value is 7. So we want to compare 7 and 8. If 7 equal to, if this item value is equal to the root data, so we have initially found the particular item, but it is not, in this case it is not true. So if it is true, we want to return that root. Otherwise, and also if it is a root equal to null, sometimes the BST does not contain anything, so then also it is returning. Okay. Next is else if it is, so in this case it is not working, so we are reached here the else if condition. If item less than root data, if the item is less, is it true? Yes, item is less than root data, so then we are only considering the left part, we are ignoring this right part. Then at that time we are again, so it is right part, so again we are calling search root left item. Then we are implementing the search algorithm to this left subtree. Okay, now this is our root. This root contains our item data, we are returning, but in this case also 3 is our root, our item is 7. Is it? So 7 is not equal to 3, so else if condition we are going to execute. If item is less than root data, root is 3. If item is less than, no, item is greater than root data, so we are going to this else part. Return search root right item. So when we are considering this subtree, right subtree of this 3. Okay, now we are ignoring 1. Now we have reached here, our root is 6. So again this is in recursively calling this algorithm search root item. Then we are checking first if item is equal to our root data, our item is 7 and our root data is 6. No, it is not. Then we have jumped into our else if condition. If else if condition is if item is less than root data, no, it is greater than root data. So if it is less than, we are executing this. If it is greater than, we are executing this statement. So we are considering the right part of this, right subtree of this root node. Again we are calling search root right item. So now we have reached here, our root is 7. Our root is 7 and our item is also 7. Then this first condition should be true at this time. Is it? If item is equal to our root data, then we are returning this root. So that is, if we are returning a node, it does mean that the item is there in our binary search tree. Otherwise, if it is not there, we are going back to other. If it is not there, let's assume that 9 is we want to search. Okay, so we have reached here, so maybe 9 was here. If we want to search 9 and we have reached 7, it is greater than. So if it is less than, so we want to reach here. Is it? So it is null. That means root is null, means that is also one of the condition that the item is not present in the binary search tree. Clear? So that is all about the searching part of searching operations of binary search tree. Next is inserting a node in a binary search tree. Okay, so inserting is also very similar to our search algorithm. So insert tree item. Tree is a name of name of one node. So first starting with our root node. If tree equal to null, if something is not there, so we want to allocate that memory. Okay, so let's assume that we want to insert 17. Okay, 17 is a new node we want to insert. So first we are comparing 17 is equal to our root node. First we want to check that if tree equal to null. If there is a node value here, if it is null, that means nothing is there. Okay, at that case, we are just allocating the memory for our tree and we are set tree data equal to item. We are creating a node and also set tree left and tree right equal to null. Okay, only one node is there, so tree left and tree right equal to null. So that is the basic criteria we want to do at last, or if you want to do at the time of insertion. Okay, if nothing is there, this will work. Okay, if nothing is there in the BST, it will work. It will insert this node as the root node of our new BST. Otherwise, this else condition should work. If item is less than tree data, so our tree data is now 8 and item is 17. 17 is less than tree data, no, greater than. So this is not going to execute, this is going to execute. That means we are only considering the right part only. Okay, so it is sure that the 17 should be in the right side of our root value 8. Now again we are calling insert tree right item. So again we have here with the value tree right 10. So our tree value is 10. If 10 is not equal to null, so it is not going to execute. It is executing this one. This condition we want to check is if 17 is less than 10, no, again greater than 10. So again this else part is going to work. So we have reached here. Again the insert procedure will call write tree, write and item. So again our tree is now 14 and our item is 17. Again it is greater than, so the left part is not going to execute, the right part we are going to execute. So insert tree right. Now the tree is 14, tree right is null. So now the insert call is like this, insert null 17. So again we have reached here. So here tree equal to null. If tree, so the step one, this first if condition is true now. If tree equal to null, allocate a memory for a tree node, and tree data is 17 and the left is also null and the right is also null. Now the insertion of the 17 as the right child of 14 is finished now. Then end of if and end of if. Okay, so the end of our procedure. That is the basic operation. That is the insertion part of binary search tree. Next is deletion. Deletion means deletes a node from a tree. So deletion is deletes a node from the tree. There are 3 different deletions is possible. Like we can delete a node with no children. Okay, that is the first case, no subtree. This is one subtree means the node with one child, and 2 subtrees means the node with 2 children. Okay, so first we are considering this. This is very easy. If we want to delete 13 does not have a right child and the left child and right child. So you can easily deallocate the memory and you can disconnect this connection, okay, without any additional action requires. Okay, you can simply just delete the node. Other second is one subtree, one child. You must make sure that after the node is deleted, its child is then connected to the delete node parents. That is the second deletion. That is if you want to delete 14 has a one left child. So the step is to ensure that we want to do this. We want to delete 14. That is 10, and so in the place of 14 we want to replace 13. So it is look like this. As a right child, 13 should be this will already deleted, and this connection is just going like this. That is the second style. The third is with 2 children. That is little difficult. So for this we want to first find the in order successor of the node to be deleted. If we want to delete 6 has 2 children, 4 and 7. So first we want to find the in order traversal. So in this in order traversal it is looked like this. So first down. So when we are reaching the down, we are selecting that. So 1, 3, 4, 6, 7, 8, 10, 13, 14. Okay, you can refer that video also. I have already created that video. I will give you the link. The in order successes, it is like this. So down, then now 6 is down, then 7 is down, 8 down now, 10 down, 13 is in the down of the 13 we have in the 14. Okay, like this we are making the in order traversal. So after the 6 it is 7. The in order successor of the 6 is 7 and the predecessor is 4. Okay, so we want to do like this. We want to replace 6 with our 7. We want to replace 6 with our 7 and we want to delete this node, and this is like this also. So first find the in order successor of the node to be deleted. After that replace the node with the in order successor until the target node is placed at the leaf of the tree. If it is here, it is okay. Okay, so we want to like this. We want to do our 7 is here and our 6 is here. So 6 is, then the target node is placed at the leaf. So now 6 is at the leaf node. So you can delete easily this 6. If you want to delete 3, okay, so what is the in order successor of 3? See, if you want to delete 3, the in order successor of 3 is 4. Is it 1, 3, 4? So we want to replace or swap this 4 and 3 here. Now 3 is at the leaf node. Then you can delete this 3. After the deletion of the node 3, our values like this. Okay, our binary search tree is like this. So that is the deletion of node with the 2 children. Okay, that is all about all the basic operations on binary search tree. So thank you.